Let's get started. Know when you can see the notebook.
Yeah, we can see it.
Okay. So where we were at last time, where we left off, is we used or in the path to creating kind of a framework for utilizing data sets, including Hugging Face data sets. We've kind of marched along, built a model, understood PyTorch NN module, used PyTorch data, built our own data loader or data set first with a length and a get item, and then built a data loader corresponding to that, and then switched to using PyTorch's data loader. And in the process, we also built the collate function. Then we've kind of moved on to using Hugging Face data sets, which unlike the PyTorch typical data sets aren't in tuples, but are in ticks. So we built the collate tick that you can see here, and also understood how the transforms of the Hugging Face allows us to provide transforms. But then the transform need to return the modified batch. And since Jimmy wanted to kind of do it in place, he introduced the concept of decorators, which is functions accepting, or actually callables, accepting other functions and returning functions or methods. And using that setup, we were able to kind of convert or generate build a transform which did it in place, but then because of the decorator, it returned the batch, and that allowed us to build the data loader. That's kind of where we were at when we left off last time. The remainder of this lecture and the next one, and most of, hopefully we get enough covered that we can touch on the convolution, but if not, at least we can finish off this lecture today. What he does in the remaining portion of this notebook is just to illustrate methods by which he improves the plotting, since visualizing many of our, whether it is the charts or the plot of the images that we are processing, is fairly helpful in analyzing what we are doing. So essentially, improvements to Matplotlib is what is covered between here and the end of this notebook. But along the way, he introduces elements of fast code, which are fairly interesting and key to how he makes that simple. So to plot the image, you take a batch and you, or you take a data loader and you do a next iterator on it, which provides you with a batch. And a batch, remember, as at least for this particular data set from Hugging Face, which is the fashion MNIST data set, has image and labels. So you pick the image portion of the batch, which gives you the XP. And then XP, because this is a batch, it has multiple items. So you select the 0th item and make that an image. And if you actually analyze the image would, or print out image.shape, it would show as 1 times or 1 2828. And since we don't want the single dimension, we just say it's a single image of a 28 by 28. Or, if it's a batch, it would have whatever number of elements are there in the batch. So we do an image and index into it so that we get the first image, which happens to be a boot. Now, the next.
Could you please increase the size, please? The font size.
Yes.
I think it hasn't increased yet, because the code is too small to be viewed by the. You can go to view and presentation mode and select presentation mode too. Okay.
Should increase the
Yeah.
there. Now that's increased. Okay. So the thing he does first, and I'll cover first what is accomplished by this particular improvement to the show image that he does. Here it's just plt.imshow, and then he uses a show image. Let's first go through the code, and then I'll also talk quite a bit about what is done with this particular decorator, because the concept of this decorator is fairly useful, and it covers a lot of stuff that is, I think, at least interesting to understand what he does with the fast core kind of capabilities. So in this case, let's first go through what show image does. So show image does the basics of IMShow, but it improves IMShow in many ways. First, it kind of says, let's put the data into the CPU. So if it's, it has the attributes, you take the image, detach it, meaning you kind of get rid of all the any of the derivatives and such, and put it on the CPU. And then this line basically says, typically images can have shape if they're RGB. In this case, it's black and white, so it's a single channel coming in, but it could be RGB, in which case there are 3 channels. And then there could be a depth, so it could then be 4 channels. And then there's sometimes an alpha, which is 5 channels. So it says, okay, if my shape is less than 5, which is kind of the typical image types of images, then I'm going to check that my length is 3, and I permute the image, because the plot and the plotting functions require the format to be H, the height, the width, and the channels, or channels last. But typically in PyTorch, the channels are first. So you need to permute the CHW, that is the image's channels, height, and width, to make the channels last, and the height and width the first 2 values. So that's what this function does, or this line of code does, after checking that it's the image is a typical image. And then if it's not an NP array, it makes it an NP array. This thing just says that if it's a single channel, then I want to index into it. If X is none, then it kind of deals with the case where you have subplots, and then put it on this particular axis or subplot. And if there is no title, provide a title. Get rid of the ticks, otherwise this annoying ticks appear on the image, which we don't want for these kind of images. And then if there's no frame, it switch off the frame and returns the subplot. Now, so that's all the functionality that he has incorporated above and beyond what IMShow has. But it's also interesting what he does here. He uses this fastcore delegates decorator. And what that decorator does is much more fully. Now let's look at the actual functionality of, so this post, and I'll post the links to it after we are done in Slack, essentially explains what the delegation problem, as he calls it, is. I'll try and summarize it. You can read at your leisure what he explains in great detail here. But the bottom line is, when you're calling functions and accepting keyword arguments as ** keyword args, then what tends to happen is, and Jeremy tends to code and use keyword args a lot in his code. And when you do that, one of the things that tends to happen is, if you are overriding, or if you're adding, as he does here, things to IMShow. So besides the parameters that he is modifying here, IMShow accepts a bunch of other parameters. But when you try to inspect the show image function, which is, you've subclassed the IMShow and are kind of improving it, then one of the bad things that happen is when you try to inspect it, it just says start keyword args. So you are at a loss as to what other parameters the original function accepted that you can still modify. And that makes program debugging significantly harder because you don't know what else is in the original function that's being set or that you would like to modify. And this delegates code that he has coded, or the delegate decorator, is able to fix that problem and provide as part of an introspection or any other help function, not just the parameters that you have changed or modified or added, but it also shows the parameters that are consumed, if you will, by the keyword argument of the original function. So that's what the fast code delegates, and within this, whatever you provide within the decorator is the function that you're delegating to, okay, from this function that is being decorated. And the code for the fast code delegates is here. So you can again read this, and I'll post a link to that. But basically, it says the decorator replace star keyword args in the signature with the params from to. So that means whatever star keyword args are in the original function that you're enhancing, it will this decorator will replace in the signature all of those parameters. So now you will get to see all of the parameters when you do introspection or when you ask for help. So for example, this code, and then let's run this code. So when you do show image, you can see that besides the AX none, fixed size none, title none, and no frame, right? After that, all the keyword arguments from the original function are also presented to you as part of the documentation. This would not happen, and you would just see star keyword args if you had not used the fc.delegates. Okay, so I personally think, and he does, I would encourage you to read through the documentation, which I just kind of pointed you to, but it is a significant improvement. And because he tends to use a lot of keyword args, argument and overrides, things in improves stuff such as in show image, this decorator is very often used by him. And I think that's definitely an improvement because otherwise it makes reading his code and interpreting and analyzing that or even actually using it effectively a big challenge. Okay, so with that done, he then goes on to show how instead of I am show, if you now use show image, you can see the ticks are gone. It's a much cleaner plot of the image. Now, this is a single image, but if you want to plot multitude of images, which we often want to do because our batches contain multiple images, then you use subplots, and you use this axis 0 or axis 0 or axis 1, which are the subplots. The subplots tell the plotting function that you want 1 row and 2 columns, right? That's what this does. Oops. Image 1 is one. Oh, I think XP10. Okay. Image. Um, so in this case, he enhances then the PLT subplots, calculates the number of rows in the returned axis grid, number of columns, calculates the width and height of the plot, the size in inches, the title that needs to be set, and then auto create an appropriate figure size depending on the rows and columns that you provide to the plot. So all of that is kind of done automatically for you. And again, the delegates is used in order to add the PLT subplots. The keep equal true, and you can kind of go and look at the functionality. It basically says keep the keyword args if I provide you keyword args in this function. NBDAV, I thought I had spoken about this earlier, but basically it's the Jemi's approach to creating a lot of functionality that you would ideally want to put in a in a module or in a package, develop it in notebooks with a lot of explanatory code and along with examples, tests, and things like that, and then use the NBDAV script that he has developed, which exports certain functionality and puts them in a module, and then you can just import that module and use all of the relevant functionality. This allows him to kind of build things, test things in notebooks, which are handy, small snippets of code, but at the same time, take advantage of script functionality and Python modules and so on and so forth. Right? So that's what the whole NBDev development structure and methodology is about. And he is, in this case, exporting functions. You can see the pound single vertical line export function or command that's added to certain cells. For example, he adds it to this cell. Another one that he adds it to is here. And if you go back to the notebooks, you'll see, for example, certain P modules are coded with that directive at the top, which means export them. And in this case, he is exporting them to the mini AI library that he continues to build through the entire course. And you can also, it also has the show doc kind of capabilities, which if you say show doc subplots provides a neat documentation of all of the subplot capabilities and the parameters that you can provide to it. And it just illustrates that you can continue. I don't know why this is possibly this issue. I did not. So now you can see that all of these, except that there's a hole here, and that's not something that we would ideally want to see in a plot. So it extends the subplot, tells it how many subplots we want. It auto calculates the number of rows and columns, removes the axis for any that we're not using. For example, in this case, if we're not using that, it gets rid of these kind of numbers and such. So again, it sets the delegates to subplots, and then it gets the grid. You can read the comments and the code. They're fairly self-explanatory. But all of these he does in order to basically provide enhancements to functions so that we can plot images conveniently and cleanly and quickly without going through a lot of calculations and manipulations with Matplotlib ourselves. So create images that gets our grade goes through our images, and then optionally, if you need titles, then show each one. So this one begins to add, in this case, you just have the images. Now you begin to add the titles if the titles are present. So you choose the labels, and then you give it all these titles, and then you show the images. Now the images even have the corresponding titles on them. So instead of just fixing the problem for this particular data set, he kind of builds in the capabilities and uses, enhances these functionality of Matplotlib. Now, one unrelated thing he does here, which we'll use multiple times, so I just wanted to kind of point out or highlight this as well. He creates an alternative data loader class building capabilities by defining a new class method so that you remember that data loaders convert data sets into loaders or generators which provide batches of data, right? So that's typically what our data loaders have done. In this case, he adds yet another way to create data loaders provided they have a data set. So you provide the data sets, you slice into them the first two, because there could be more than two if you also have a test data set. In this case, there are just two. So you take them, split them into train and validation. And then again, I'll also post some links to class methods. Class methods are typically alternate class constructors. That's what class methods typically are used for. In this case, the alternate class constructor is from DB. So you'll see subsequently in subsequent notebooks, you'll see he will do you provide a data set and then say from DD, that means from the data set dictionary, the first, because this is a class method, unlike an instance method, the first argument to a class method is a CLS, which is the class, instead of what typically is provided to an instance method, which is set. Then you provide it the dataset dictionary and the typical things which are needed for a data loader, that is the batch size. You tell it, do you want the data loaders to be tuples, or do you want them to be dictionary outputs as well? And so you can say as tuple is true, and then the keyword adds whatever that are being utilized. So you take, for example, a function collate dict, which takes the train dataset dictionary as the input for the collate function, and then you just say return the class, which means return a class of data loaders, star get DLS, and we have seen this, and he uses these kind of constructs a lot, so it's important to get familiar with it. Star get DLS basically says get the data loaders, each one of the data loaders, and as a single item, if you will. And then the star dd dot values basically again unpacks the values from within the data set. So those would correspond to these self.train and self.values, and the values coming from the data set, then the batch size, the collate functionality, and the star.keyword. So you'll see the utilization of this in a subsequent notebook, and that's the reason he exports this functionality as well. And I'm just
why is there a star here? A star DD? Is there the star get underscore DLS? Is it some pointer?
Yes, because you're creating. Yes, because you're creating. So remember that the dd.values, if it's a data set, will have the dataset train, dataset valid, right? So you would get the data loaders corresponding to that. So the class of data, what you're building is the data loaders for all of the values that are there in the dataset dictionary. And it'll become obvious when we use this function. So when we use this function, let's I would say hold, or let's revisit that question, and the answer will become much clearer when we actually use this method. Okay. And what we pass in will be the dataset dictionary. Okay. And the dataset dictionary has values, and it says pick those values and unpack them and provide them as unpacked items to the get data loaders, and the star get data loaders says, again, whatever data loaders you get, unpack them and return them from this method. Right. So since this is in, I'm explaining it in concept, but when we actually see the usage of it shortly, we'll understand that. So the next time we use something from DB, remind me and I'll explain why this star DB.values is necessary. Okay, so having done that, the next set of explanations in the notebook is completely about callbacks. And these callbacks and the concept of callbacks, it becomes very important for us in building up all kinds of flexibility in our training group. So let's kind of visit this notebook. The whole purpose of this notebook is to explain the use of callbacks, what they are, and how he intends to use them. And we see the actual usage in the subsequent notebooks. So while that's loading, typically callbacks, and I am not a GUI or a web person, so he explains that the most often used purpose of callbacks is in GUIs, and typically you can do, and he kind of illustrates that with importing IPy widgets or IPython widgets. And there is a widget in the IPython widget called button. So you can import IPy widgets as widgets, you can import a widget button. And if you have a button and you say the description of the button is click me, then it provides click me as a button. Now, what I would like you to notice though is when I click it, nothing happens, right? So it's just a button, but nothing happens when I click it in the click me. The way callback works is let's define a function and pass in a parameter O, and the function just says print hello. So we have defined this function. Now what we do, and a typical use of callback, is to pass in this function to the widget, because the widget has an on-click callback, and to that callback, if we pass in a function which we have defined as just saying print hello, then we enable the click me button to execute the function when I click on it. So now, after having provided this function is the callback function, and we provide that function to the on-click callback, right? So on-click, call this function is what this particular line of code says. And this function obviously says print hello. So now, and I had illustrated to you that when I click this function before, there was no callback registered with it. That is, there was no function that it was executing. So even though it had the on-click callback, but basically there was no function there. Now that we have a print hello function, if I click on it, you can see the printing of hello. So that's kind of how in the GUI world callbacks are used, but he'll illustrate and build up ultimately parameterizable, flexible training loop using callbacks at every step of the training loop, as we'll see when we go into building the learner, but we'll get there step by step. So he kind of wants to explain the creation of callbacks, because this is important. A lot of, if you want to modify the training loop and add capabilities to the training loop, then we do that, at least in this context and in the library that is building, through the mechanism of callbacks. So let's understand how such callbacks work. So let's just bring in a simple sleep function from time, and let's code a slow calculation. So all that slow calculation does is initializes a result. And then for the first four integers for I in the range of 5, so 0, 1, 2, 3, 4, so the first 5 starting at 0, result is computed as the square of I. So for example, it will be first 0 square, 1 square, 2 square, and so on. And then it sleeps for a second, and then it returns the result. So you would see it executing, but that's the definition of slow calculation. So when we run it, you can see that there is a delay, and there'll be a delay after each calculation, and then it now because there's a second of a delay for each of the square computes. So 5-second delay before it prints the result, and 0 to 4. So if you add up 4 square, 3 square, 2 square, and 1 square, you end up with 30. Now, let's say we define callbacks to be CD, and we pass in none initially, and we use a callback within the function. So we say if callback, then call the actual callback. So if there is none, obviously there'll be no callbacks here, so the function executes as normal. If on the other hand, we provide a callback, that callback will be executed, and the callback will also be sent in the value I, which is the index that's used in the loop. Any questions of how this works? So that is critical to all that we do subsequently. So now we code show progress, and then this I, which is the index of the range function, is we can label it as epoch, and the print function that what we tell the show progress function to do is say, awesome, we have finished epoch, and obviously the number of the epoch, right? So that's what our show function is defined as. And now if we pass in the show progress function in as a callback to the slow calculation function, then the slow calculation function will come to this point in the code, if callback, and there is a callback, because if this is not none, it's now show progress. So this is non-zero, so it will execute this function, which is show progress I. And when it does that, then it will print this line. It will say, awesome, we have finished epoch, and the I is what is passed in as, so the epoch will be I, and so it will print 0, 1, 2, 3, 4. And then finally, it will return the result, which is print. Any questions on why and what it's doing here? If not, let's keep moving. So instead of defining a function like show progress, which is actually a function F, and you have a name for it, you can pass in a lambda function, which is basically a function without a name, if you will, and again do the same thing. And we pass in the parameter O if I, and it will again print the same thing. So instead of saying show progress, we can just send in to the slow calculation lambda function, which becomes our callback. So that again does exactly the same thing as before. It's just that we have replaced show progress with a lambda function. We can use multiple values defined in our show progress. Now, instead of just using epoch, we are using exclamation, which is also a parameter, and epoch. And then the exclamation is whatever we pass into it as well. And then we have finished epoch. So now we change the definition of show progress to include 2 parameters. And this is the use of partials in coding callbacks, or in general use of partial for any function. So basically, partial says you fix some value of the parameters in a function and then call the function using partial, then those values remain fixed. And when you call subsequently the function, then only the non-fixed parameters have to be passed. So for example, any kind of switch is which I don't like, but anyway, the function here that is passed is a lambda function, and it just has a single parameter, O show progress, okay, I guess. And the okay, I guess, is what will get printed here, and as the exclamation. And we have finished epoch is actually part of the show progress function, and the epoch is printed. And this is something I added to illustrate how exactly to use partial. So slow calculation, partial of show progress, okay, I guess, is what you would ideally like to use in setting up show progress, which means now when you've done partial of show progress with okay, I guess, that means this function is hard coded with an exclamation of okay, I guess. And so when you subsequently call show progress, you only need to pass it epoch because this has already been hard coded by using the partial. And it has the same effect. So it says make. Now, the other way to do it, one way to do it is to use partial. The other way to do it is to use a function which returns a function, again, a decorator in a sense. But you could just simply use partial. This is just another way to incorporate the same thing. So, or to implement the same idea. So what it does here is it creates a function called make show progress, to which it passes exclamation. The inner function is the one that gets returned by the make show progress function. The inner function that's returned has the hard-coded exclamation. And so now to the inner function, you just need to pass the epoch value. So you can do it with partial, which I prefer because it's a lot simpler. But again, you can also do it by defining a function that returns a function. And you can, again, slow calculation, make progress, nice, which means that exclamation has been fixed to nice. And then subsequently, when you call it, you just have to pass it the epoch number. So that. So these are just illustrations he shows of usage of partial to set up things in functions. Ultimately, the goal is to illustrate the various ways you can code callbacks, right? And you can always call it or name the partial function as f2 and then call f2, or passing f2 as not call f2, but passing f2 to slow calculation or as the callback function. All of these essentially have the same effect, right? Just variations of how you set up the callback function. Now, so far we have always been using functions as callables, functions as callbacks. But here it begins to show that you can use methods or a class also as a callback. Because remember that classes can also be callables, right? So callbacks as callable classes. And the way you code a callable class is you add that undercall. So an instance of progress to callback is then called. If you call it with the brackets, then it will do or execute this portion of code. So that portion of code or that line of code is exactly identical to the function, right? So we use the init method or the initialization of this class to set up our exclamation value. So essentially what we were setting up here using partials, we use the init in a class to do that. So now it will say awesome and then print it. But you can't override it because ultimately whatever is passed in to the initialization function of the instance creation will be what is used as the exclamation. So for example, progress showing callback class initialized with just super, and that becomes our callback. And so now what that means is an instance of this function, this class has been created with exclamation being just super. So the callback is an instance of this class with the exclamation being just super. And now when the callback is passed in And when it is called by the slow calculation code, CB this line of code, it will consider in exclamation, which is just super. We have finished. The other thing you can begin to do now is, instead of just passing in fixed values like
Srinivasan, your voice is breaking up.
oh, okay. Make sure I'm close to the phone. Can you hear me better now?
Yes.
Yeah, much better.
Okay. So here he's just illustrating that you can use the callback functions, just illustrating the role that star A and star B, and typically the again by convention what's used as tags and keyword tags. Basically, these conventions you could end up using whatever you want, like it was here, but the convention in Python is to use star tag and star keyword tag to pass in position.
Breaking again. It's very hard to figure out what you're saying. Sorry.
Yeah, it's breaking up again. It's hard to hear anything that you're saying.
Okay, hang on a second. Let me of my phone. Can you hear me better now, or is it still bad?
Yeah, this is much better.
Okay, if it degrades again, give me a minute, and I'll probably am using headphones, and maybe their power or something is degrading. In which case, I'll switch.
Right.
Okay, let me know if it happens again. Okay, so here he's just illustrating. Let's use a function star A and star B, and the function code says print args and then a dictionary with values in A, and print keyword args and a dictionary with the values in B, right? And then let's say we stick in 3, the string A, the integer 3, the string A, and thing1 equals hello. So he wants to illustrate what are the things that go into A. And remember, this would be typically star args and this would be star keyword args. But it doesn't matter, that's more of a convention. But what results when we call F with 3 and A, and then the keyword string and hello, is these values get combined into A as a tuple, right? So these all positional arguments get combined in args, and all keyword arguments that are provided will get combined in star keyword args, or actually I should say in keyword args. So that's what happens when we pass in or call star args and star keyword args. All positional arguments get combined into a tuple in args when we are passing it, but when it's called, the args get unpacked into the individual arguments, right? As we'll see in a minute. So here you can see that args is the tuple made up of integer 3 and the string A, and keyword args is the dictionary thing1 and hello. Now, let's say we define a function g, a, b, and c default to 0, and we say print abc. Right? Now, let's say we define args to be this list 1, 2, and the keyword args is a dictionary of c equals c is 3. Then when we call G args or G star args means when we're calling the function with star args, that means that each one of these values in the list is individually passed to G, right? It unpacks the values in this list, passes them to G, and therefore G has now, obviously, if you do this, you need to be, or if you particularly are doing it using this kind of example, then the number of parameters here should match what is being sent to it through args and keyword args. Otherwise, the function will not work, as I'll illustrate in a minute. But right now it does, because when you split star args or when you unpack the arguments, there are two arguments, and the two arguments are passed to the two positional values A and B. And then when you do the star keyword args, then it basically says split this and give me what is in keyword args, which is the dictionary with value C. The value C is 3 instead of the default value 0, so it will print 1, 2, and 3, right? But for example, just to illustrate, let's say I do this, then you will see that it complains and it can't execute, because now when it tries to unpack, it gets 3 values here, whereas it can only handle 2 parameters. So it will say that there is an error. It got multiple values for argument C. Now, what error it reports is that it says that it got multiple values for this, whereas, but the source of the error is here. The fact that we increased this. The same thing will happen if we play around and increase the number of keyword arguments as well, as we'll see in a minute why this is relevant when we deal with it in the actual callback. So we're back to the slow calculations and how what we saw matters to us. So again, let's define slow calculation, and now we are defining 2 methods within our callback function that we are passing. We are first going to say one method which is called before the calculation, so before it does the calculation, and another method of the same callback which we want to execute after the calculation is done. Okay, and again, this before and after concept that you're beginning to introduce will be very useful, because as you can kind of probably think about, we want to do some things before we begin to fit, some things before we form the batch, some things before we run an epoch, and some things after we have created a batch, something after we have built after we have run a single epoch, and some things after we have completed running all of the fit functions. So that's the reason it begins to introduce this concept of before calc, after calc, because you will begin to see before batch, after batch, before epoch, after epoch, before fit, after fit. But let's see how it's actually done with a very simple example. So we say the callback has 2 attributes. Before calc, pass it just a epoch value or the range in this case, and then here we are passing it 2 values, not just the value of the range or the index, but also the actual value that's calculated as a result of the calculation. Okay, so that's the new definition of a slow calculation, which begins to have 2 epochs as part of, or 2 methods as part of the same callback that we begin to use. Now we define a print step callback, and we define 2 methods in that callback. Okay, before calc, and we pass it in star args, star keyword args. So we don't essentially tell it specifically which argument we're passing. We just say, hey, assume we are passing you a bunch of arguments as positional arguments and a bunch of arguments as keyword arguments. And here, in this particular instance, since we're just starting, we don't use them. We'll use them in the next step. So it just says print about to start and done step. Okay. So you can see, or at least I would say, first think about what should, even before we go to the next cell, ideally you should think about what would happen when this callbacks are included here. So just to think through it, once we provide an instance of a print step callback, it will come to this part of code, if callback, and obviously we passed it a callback, so there is a callback. Then callback dot before calc, so it comes and executes this lines of code, and it says about to start. So before it executes I is 0, it says it will print about to start. Then it will calculate this, come here, it will execute this line of code, it will say done step, right? So you can see that that's essentially what happens when we execute this line of code, right? It prints about to start, done step, about to start, done step. And actually, you can also see the delay is between the about to start and the done step, because the second is right here. So if you run it, you'll see that about to start will print, there'll be a short delay, and then it will print done step. And then eventually it just returns the result, which is 30, right? Now let's start to use some of the parameters, which is where the star args and the star keyword args comes in, right? So here we are passing in a positional parameters, which is epoch. In before calc, we just used I, so that's corresponding to the epoch. There's nothing we pass in as a keyword parameter here. So we can just say about to start epoch, and of course I modified it from what we had. I modified this to make it clearer. About to start epoch, and then it prints the actual epoch. And here we pass in epoch and the value, right? So print after epoch, and the value is value, right? So now you pass in this callback to the slow calculation, and you can kind of think through what will happen in this case. So it will say about to start epoch 0, after epoch 0, the value is 0. And it gives you a much more detailed description of what is happening in the code before and after every calculation. Right? And one of the things that I would encourage you to do to see whether you understand star args and star keyword args is to play with this and, for example, remove or one of these and see, for example, what happens. Essentially, if you have a print step callback and you do not have star args, in this case, we are not using keyword args in any instance. So if you change keyword args, that really doesn't matter. But if, on the other hand, you remove star args from here, given that you will need a positional argument, it will obviously complain and it will not run successfully. So again, I would encourage you to play with this, remove star args before the calc, star keyword args from another calc, and see what happens, right? To ensure that you understand the usage of star args for all positional values and star keyword args for all keyword values or dict kind of values. Now, so far, what we've done is just done things which are informational. That is, it just says, I'm just starting and printing, I'm about to start, and after I start, this is the value, before I start, this is the value, and so on and so forth. But what we could do, and in fact, is often the more useful part of callback, is if we can go in and change what the actual function is or the results that are being executed or the function that's being executed, if we are able to modify the behavior. So let's see how that's done using callback. So now we are defining a slow calculation function, again, with a default none callback. And we say if the callback, if there is a callback and it has an attribute before callback, then call it. Right? Then do the results, sleep. And here is the tricky one where we are actually modifying the behavior. So if there is a callback and it has an attribute after calc, this is the tricky part. If this is the case, this line is identical to here, but what we do here is the interesting thing. We say if callback after calculation and we pass it the two values, the I and the result. That's nothing new. But here, what we do is, what is interesting is this line, by the way, if cb dot after calc I result, right? This is actually, and we'll see when we look at the code, this line is an if test, and it tests a flag. Okay, and the flag is set by the call to the callback, and I'll explain more in detail when we actually look at the code of the after calc. So this code will execute if this is true, right? So if our callback returns true, then we execute print stopping early, and we break from this loop and get out and print the result. Okay, so this line is actually a flag check. Okay, that means that in the after calc method, besides what we used to do before, we can actually do something different, right? So after calc self epoch val, and we are doing nothing in before calc. So before calc will not execute at all because the method doesn't even exist here. But let's focus on what we do in the after calc. So in the after calc method, we pass it the epoch and the validation and the value. It says after epoch value is value. And this is the key part. If value is greater than 10, return true. So let's kind of run this code, run here, and think for a minute what will happen when we pass this callback to the slow calculation function. Kind of mentally work through the code and then see whether the behavior is what we expect. So the first part is, because there is no before calc, it will obviously do nothing. It will just fall through this code. This will not execute. It will not execute because this callback doesn't have an attribute before calc. So this line is not executed or skipped. It comes to result. It calculates the result. The first case is 0. Sleeps for a second. Then it checks this. If callback and has attribute after calc. Oh, it does, right? So this callback has an attribute after calc. That means it will go to this method. The method now says print after epoch. So it will print after epoch val is 0, right? Then once it's printed that, it also checks, it says if callback after calc I result. Now, this if statement doesn't return true, right? Because it will only return true if the value is greater than 10. So that means this portion of the code is not executed and it goes back. Right? So it then goes back to re-evaluate the next epoch. So for I in the range of from 0, it skipped to 1. So it calculates, goes through this line of code again, calculates it for 1, sleep, comes here, again, it does print, checks if value greater than 10. No, the value is still not greater than 10. It's just value is just 1 because you just added 0 to 1. So again, this doesn't return true. So it again goes back here and it continues until the value exceeds 10. So the value exceeds 10 when, and this is the reason I added this thing to print the value as well. So after after I is 3, you calculate the value and the value is now 14. So when it comes to calling this, and after it has printed the value is 14, it checks is the value greater than 10? Yeah. At that point, it returns true. And because it returns true, this line, if this will return, so this will become true. This particular, that's why I called it a flag. This callback after calc I rest will become true only after the index goes to beyond 3. At that point, If true, it will execute these two statements, print stopping early. So it will print that, and it will break out of this entire thing and return. Right? So now what we've done is we've modified the behavior of slow calculation by having a callback and using the callback as a flag and doing something different within it. Now, there's not the only way to do it, but there's just one of the ways in which we can do it, right? So now if we call slow calculation, and I went through what it does, so it'll print this, print 1, print 2, print 3, and it'll stop. Any questions? Okay, if not, let's keep going. So now we define slow calculator and put the callback as well as the calculating function, all of it in the same slow calculator class. Instead of having a separate slow calculation function, we just put it as calc method and define a callback, give it a name, give it some arguments. And if there is no callback, if self.callback doesn't exist, it just returns. The callback says get the attribute of the name, which could be, for example, before calc, after calc, things like that. And then if there is a callback, return the callback, obviously self, which means an instance of it, and with the arguments passed to it. Okay, so this is just incorporating all of the things we have done, but within a single slow calculator class. So that class has a callback, that class has a calc method, a callback method, and it's initiated with callbacks and a result value, which in our case is 0. Then we create a modifying callback and add an after calc method. And we pass in the calc and the epoch. And we basically say in the after calc, pass in after epoch, the result value is whatever the calculated result is. And here we begin to change things that are happening within the slow calculation class itself. So how do we do that? We say this line is similar to what we did before. If calc.result is greater than 10, then return true. So when the if self callback after callback I flag check is done, then it will execute this code. And as long as this is not true, this flag will return false, which means that this whole chunk of code will not be executed, and it will keep going back to execute the next range step, right? But we can also not only modify it then, but we can also modify what it does in each of the steps, because look at the next line of code, what it does. If the calc.result is less than 3, which means for 0 and for 1, nothing will happen, right? Because for 0 square is 0, 1 square is 1, and we add the 2 and we are still at 1. But once we get to step 2, it will do 2 square, which is 4, and it will add that to the 1, so it will get to 5. And that means if for the first 2 steps, we do nothing. But from the third step on, by the third step, I mean the value of the index is 2, then if calc.result is less than 3, then do nothing. Sorry, the other way around. If calc.result is less than 3, then we want the calc.result to be 2 times the calc.result, right? So for the 0th and the first index, for 0th index, it still doesn't matter, because when we calculate the result, it will be 0. So 0 times 2 will be 0. But when we calculate it for the second index, then which is 1, then calc.res will still be less than 3, because we are adding 1 to the previously calculated result, which is 0. And then we change the result value. So instead of just having the value as 1, we make it a 2. Okay? So a 2 will get added. Instead of adding 1 to a 0, we'll add 2 to a 0. So we are modifying not just when we stop, but we're modifying this calculation itself. That's yet another capability or yet another thing we can do by using callbacks. So callbacks are very powerful in that sense because you're actually modifying the result of the calculations that are going on that you're trying to report on, but it's not just reporting, you can actually modify the behavior. Okay. So now if you calculate slow calculator, modifying callback, right, an instance of the modifying callback, and you call the calculator's calc method, which is this method, which is the thing that runs this, and print the calculator result, then here's what you see. After 0, the result is 0. After 1, the result value is 1. But after 2, the result value is 6. And the reason that this is 6 is because of the modification we have done here. Right? And after 3, the result value is not 14 as we saw earlier, but it's 15. And because the condition is now satisfied, it will return true and will stop early. Right. So again, this just is, and I'd encourage you to go through and figure out exactly how this works. The tricky part, at least for me, is understanding the fact that this line and the corresponding line is actually a flag. That's a little bit of something that you need to wrap your head around, that the way he has coded it, if it's a flag, so unless it returns true, this whole thing wouldn't be executed. Going until this condition is satisfied, and when it returns true is when these lines are executed, so it breaks out of the loop. And that's important to understand because he also uses the setting of these kind of flags in the actual callbacks that he codes for the training loop. So this is kind of an illustration of the details of how callbacks work and how he intends to use callback, not just to print, although in several cases that's useful because it helps us debug and also tells us what's going on, but it also is extremely useful to modify things. So for example, modify the batch if you're doing something before the batch, after the batch if you want to fix something, or after an epoch if you want to report on the statistics, but also want to fix some things, combine losses, for example, things like that. After every epoch, if you want to do certain set of functionality, you can think of the variety of capabilities that this kind of callback coding begins to provide us, the ability to modify the training loop. Any questions so far on usage of callbacks? Am I clear?
Yes.
Okay.
So I was just going to make an observation that, like Keras has these before and after epoch kind of callbacks built in. Also, I believe PyTorch Lightning might have, but I'm not sure. I haven't used Lightning that much.
Yes, PyTorch Lightning is very similar to what FastAI did or does. So in fact, there was a little bit of a brouhaha when Lightning came out saying, hey, how is this any different from things that I've already implemented? And, why is this kind of new and so on? Of course, FastAI did a lot more, but sometimes, and I agree with that criticism of FastAI, sometimes it did too much. So it hid so much from you that you were kind of at a loss as to what is going on, and debugging it because of Jeremy's coding style can sometimes be a problem if you're not really up on Python skills and stuff, and he uses quite a bit of fast core. So I think given all that, he's begun to, possibly the next rev of FastAI, as he says in the lessons, will be a version of mini AI. So he kind of threw away much of the, hiding abstractions that he did, and kind of has begun to take a slightly different approach, I think, in mini AI, as we will see as we go through the rest of it. And he does a lot more than just the callbacks. He also uses decorators to make the callbacks a lot simpler. And it's kind of both interesting as well as somewhat confusing, because he initially tries to use the with constructor and in setting up the callbacks, finds out that he runs into some problems with the usage of context managers and switches to using the decorators. He starts with decorators, switches to context managers, switches back to the decorators. So if you just listen to the video, as I have been doing, it's somewhat confusing because the video and the eventual code you end up with don't match. But if you go ahead and listen to subsequent lectures, you kind of get an understanding. Okay. Oh, he switched to using decorators again because it didn't work what he was trying to explain with context management. But on that note, I would really encourage people to get very familiar with the decorators, context managers, and the next thing which he begins to touch on, the magic methods, or what are sometimes called the dunder methods in Python, because he uses them heavily to modify the code. And if you are familiar with them, it makes what he does very simple and easy to understand. If you are struggling with what is going on, it seems a lot of gobbledygook, or not easy to understand. And as he says, the reason to get familiar with decorators, with context managers, and with these dunder methods and magic methods is because of what he describes correctly as. Otherwise, you suffer from cognitive overload, which, for example, I definitely suffered from, not being a native programmer and not having formal education in programming and stuff. But I've had to go through multiple versions of his course by now to become familiar with these things. So I'd highly encourage you to play with these offline, get familiar with their usage. So here he just kind of gives you a very simple example of some of the dunder methods. The big thing in Python, I'll again post a couple of links on, is attributes, how the attributes are managed and what they are done, how the various dunder methods actually work. So he defines, for example, a sloppy adder, and a sloppy adder basically says, if I initialize the class with O and self B, so I just pass in to dunder add the B value, then you return the O and B.O, and you also add in a value of 0.01 and make that a string when you print it. So if A is sloppy adder, so that find the class. So if A is sloppy adder 1, then you just made self.o to be 1, and B is sloppy adder 2, so you would make that a 2. And when you add A plus B, then this plus actually causes the invocation of the dunder add method. So you say A and B get, so self.o and then B.o, and you add in the 0.01. So that's why you see the 3.01 here. Several things he uses throughout is the getAttr and the dunder getAttr and the getAttr. So these are again methods that are used to access attributes in Python. So for example, let's say class A is defined as with the values class attributes of A as 1 and B as 2. Then you instantiate A, and instance dot B is obviously the value 2, right? So that's basic Python. And you can access the attribute B by saying get the attribute from the instance B, and it will return 2. But what he points out is, it's not like the attributes in Python can't be changed. You can actually change it even as you're getting it, regardless of what the value is here. You can say get attr, which means you'll go and try to grab the attribute B from the instance of class A, get the attribute B, but do the following. Get the attribute B if random.random is greater than 0.5. That means if, depending on the value that random.random returns, get the attribute B, depending on this value, get me A. That is, if this value is greater than 0.5, then it will return B, so it will return 2. If this value is less than 0.5, it will return A. So if you run this a bunch of times, you'll see that this value that's returned will change. So now it's returning 1, run it again, it returns 2. So you can change what the attributes that you get back from an instance of the class. Here's another example of how he just says what is going on when you do the getAttra, when you execute the getAttra function. So class B defined with these attributes. You define the getAttra, whatever value you pass to it. If it's not, doesn't begin with an underscore, then, it does begin with an underscore, raise an attribute error with K. Otherwise, return hello from and K, whatever you pass in here as the attribute that you're seeking. So you define the class, you define B, then you say B.A, obviously it will give the result 1, right? And B.foo. Now foo doesn't exist in B. So then it'll go here, A is passed in as foo, K0 is not that, so it won't raise an attribute error, but it'll say return F, hello from foo. And if instead you say C, then C also doesn't exist. So the getAttra is the method used when you want to get an attribute, or you can state it the reverse way, that getAttra is what is used when an attribute doesn't exist in the class. So when you try to access an attribute that it doesn't exist, and you don't have a getAttra, then it will just report an error. If on the other hand, you want those attribute accesses to do certain things or to return a particular behavior, then you can code a getAttra method within the class, and that method will get executed when you access an attribute that's not defined, right? The reason this is important is, remember that in the callbacks, we used the after calc and before calc and so on as they were methods. But again, methods are basically attributes of the class as well, right? So in that sense, it's important because you can, by defining getAttra, you can define what to do when those attributes don't exist. So that's the reason he has kind of illustrated some of this playing with the attributes. But in general, I would definitely focus on these. The enter and the exit are context managers related. The new is something that is used in order to create a class. For the longest time, this was something, because new is not often used. Init is what is used when we define a class, like, for example, in this case. And often people refer to init as a constructor, but actually it's more precise to say that init is an initializer, because once the class flow calculator, just this line actually calls new to create a class. So that's actually the constructor of the class, new. And init is actually uses the class created by new and shoves or sets it up for further use by the method. So it takes, this self, which is an instance of this class, it begins to exist only because the new has already created a namespace with the class. So that's what this new function is. we don't use it often. Invariably, we just use init to initialize the class, but new is actually the class constructor and init is the class initializer. And then get item is, as we have covered before, is what allows us to access the attributes, or in fact, in dictionary, the and the square brackets in the arrays, the slice we provide or the indices we provide is what is used by get item. We have already seen get attr and set attr, which set attr is kind of for setting the values of attributes. Get attr is, under get attr is when we want, or what do we want to do when we access attributes that don't exist in the class. Delete is for deleting attributes. Init is for initializing the classes. New, as I said, is for class construction. Enter and exit are used in context managers, and context managers is an entirely new, entirely different discussion. We'll get into it a little bit when we look at a couple of lectures down the road when we start using them. Length is fairly simple. It just returns the length of the elements. Wrapper is what is used to represent or the print out what's the definition of a class. And the dunder string method is the string. And dunder string and dunder wrapper are the two representations that are used typically to represent a class. And dunder wrapper is often the preferred method to represent a class, because if you don't define a dunder string, that falls back to dunder wrapper. So if you want to only define one of them, choose dunder wrapper, because dunder string will fall back to dunder wrapper if dunder string doesn't exist. Okay, that's like, you know, a very, very cursory summary of the magic methods, but I would encourage you to go spend a lot more time. Any questions on this?
Do you know why init is used rather than new in terms of including all the usual instructions?
Sure. I think this is my, you may want to refer to books. This is, and you know, people, Sujit and Yuri and stuff have used it, Python probably a lot more than I can also answer. But my opinion, Emily, is that it's not often that you want to change something in new, right? That you just want an instance of the class or the class to be created. So you don't often have a need to change that under new. On the other hand, when you create a class, what you care about is what you initialize the class with. So that's the reason you see dunder init and all that. But very seldom do you actually need to change what a class constructor does, right? Because you just use the class that the constructor returns and you initialize it with the values, and then you create the methods and so on. So I would even want to see, of course, I've seen it when he has done the whole FastAI2 explanations, but in this course, I would again want to wait to see where he actually uses the dunder new method and why he feels that's important to know. Because very often you don't, or very seldom do you need to use it, right? You just use the created class, that namespace that the new returns. And what you fill it with is what matters, right? Which is these values and then these methods, or these attributes and then these methods. Any comments, thoughts, Sudeep?
I was actually, while you were speaking, it kind of struck me too. The first thought that occurred to me was that, when you do new, it just allocates a pointer in memory, right? And that's it, nothing else. But when you do init, it allocates the actual space that would require. But so then I started wondering where we would do such a thing. I mean, it's by default you always allocate a pointer when you start, right? So and that is like, it doesn't depend on the class. So I was looking at Bird. I haven't got a good answer here. So I can, well, yeah, I basically tried to look for Python when to use new instead of init. And it says, and I don't know why it's it says use new when you need to create an object that is not a subclass of object. So again, I am not sure, if there is such a thing which is not a subclass of object.
Yeah, that's why. Yeah, exactly, because everything is a subclass of object eventually in Python, right? I mean, that is the thing. So yeah, I'm interested in finding out the case MD of where Jeremy uses new and why is it new. But in all my experience, at least, unless you are dealing with some complicated cases, that is very, very seldom, unless you're dealing with metaclasses and stuff, which help to define how a class is constructed. In that case, you definitely need to change and modify the new. But that's metaclass, which is how to change the construction of a class itself and change the properties of a class. But most often when you are dealing with Python, or you're just interested in changing the initialization of a class. But so to answer your question of, I'd reverse it to say, I'd be interested to see where he uses new, because very often we can just work for most purposes under init suffices. The one instance where it will not is when we're using metaclasses, which means we are beginning to change what a class constructor does.
Interesting, thanks.
Yeah, here is a Medium article, which basically says, what Srinivas said. If you want to kind of intercept between the new and the init, right? You want to add additional behavior. That's when you would use it. And he gives you an example here. It's kind of a contrived one. He's basically trying to lowercase your input arguments. But yeah, you could do it in the init method as well in a subclass. But
right. So that's why I said that, I'm eager to see the example of where he uses it under new and in a practical sense, make it relevant. I have seen uses of under new, but every instance I've seen has been a case of meta programming or meta class. That means you are wanting to change something in the construction of the class, which is very, very seldom the case. Okay, quick question for all of you. Should we start and at least try and get through some of the convolution basics, the next notebook, or should we stop here and start with convolutions the next time? I'm fine with either.
I have no preference. Either one's good.
Same.
Okay, sorry, go ahead.
Also no preference.
Okay, so let's keep going because we have taken more time in going through some of the details. So at least I'm going to attempt to go through the convolutions lecture. We'll see how far we get, and if not, we'll restart from the beginning. Okay, so the next lecture, and it's somewhat unfortunate because we use callbacks and stuff, and we kind of go through convolutions, try to understand them, try to kind of create an autoencoder using convolutions and for the fashion MNIST, and run into some problems. And at that point, switch back to building the learner framework, but the learner framework is just his language for building a framework for ultimately flexible training methodology. Okay, so it's somewhat of a detour because some of the things we saw in callback, it'll be a couple of lectures before we return to its usage, which I think is somewhat unfortunate because then, the context is lost. But that's the way his lectures go. So I'm going to continue to follow that for right now. But we can return to kind of the callback code and look at them if we have any questions as and when we do that. While that is running, let's, again, he just sets up a bunch of imports, uses we are switching back to the MNIST numbers data set for this particular example. And we are going to essentially look at the basics, the very basics of convolution. So what is a convolution and what happens, or what is attempted to be done by the use of convolution, the math of convolution and the concept of convolution when it comes to deep learning and so on. So the basic stuff that we are trying to do is to try to recognize different portions of an image. So, what we're trying to do is detect features in an image. So he defines a feature as a visually distinctive attribute. For example, a number 7 is characterized by a horizontal edge near the top of the digit, as you can see, and a top right to bottom left kind of diagonal edge underneath that, right? So the flat top of the 7 and then a diagonal stroke. So finding edges in images is a very important task and is surprisingly straightforward. So we can do that using convolution. So convolution is nothing else but just multiplications and additions. And I think the interesting part of it is to look at the image for a convolution. And let's look at right. So when we say convolution, what we do is we start with things called filters. So let's assume that a filter is just a 2 by 2 value. So we have values alpha, beta, but these 4 values for the filter. And this is our actual image. Now, in our case, since we are just using black and white images, these are just single values. If it were an RGB image, you would have 3 slices, a red slice, a blue slice, and a green slice. But let's ignore that for now. Let's just assume this is a single flat 9 input value of a 3 by 3 slice or chunk of our 28 by 28 image of a digit. Now, when we say we are applying a convolution, then we take a filter, which is composed of a 2 by 2 value, and multiply these values with these values to yield a single result. So he shows that in here, if I'm not mistaken. So this is the multiplication that I'm referring to. So what happens is you multiply alpha times A, beta times B, whatever this is, times B, and then delta times E, and then you add in a bias to generate the first value P. You take the same alpha, beta, Y, and delta to generate Q. Take the same values, except you're multiplying. Remember what changes? It's the same values of the filters. You can see alpha, beta, Y, and delta in each case. What is changing is these A, B, D, and E for the first value, B, C, E, and F for the second, D, E, G, and H for the third, E, F, H, J for the S. So going back to this, let's look at what that corresponds to. So that means these 4 gives us P. Then you slide the filter one step to the right. So that's why in the multiplication we saw the second multiplication was alpha times B, plus beta times C, and then this times E, and then this value times F to yield Q. And the same values multiplied by, after we have moved this filter, first we start here, one step to the right, then generate Q, one step down, generate R, one step to the right, generate S. So this is what applying a filter to an image means, right? And this operation, this set of multiplication to generate these pixels is what is called convolving this filter with this image. Okay, so that's fundamentally the concept of a convolution. You take a set of values which are described in a filter, you multiply the image portions, you locate the filter on the image, multiply it, provide the result, shift it, and that's the amount by which you shift is called a stride. So here it's stride 1 because you're sliding it or striding it by a single pixel value. You could slide it by multiple, in which case it's called slide 2, slide 3, stride 2, 3, or 4. Typically, it's usually stride 1 or stride 2. And in this case, it's stride 1. These are filters. This is the image. Okay. So that's essentially what is done in when we convolve to a filter with an image. And as he points out, this particular CNN from different viewpoints post, that's this guy. This post is really very, very useful in understanding the details. So this is called a filter. This is the image. Since the filter fits the image 4 times, we have 4 results, once for each set of multiplications. And it kind of lays out the equational view, right? And if you want to do it as the compact view, this is what it is. I would again encourage you folks to kind of go through and look through this, make sure you understand all of the different details. Also the fact that you can unpack or unroll these, right? Because he eventually gets to this unrolling. You can lay out the filters in this way, fill it up with zeros, and basically you have just unrolled the filter and unrolled your image, and that makes the multiplication a much simpler thing to do to generate the 4 pixels. We'll get into a lot more detail of this with actual example that makes it very clear. But here is a simple example of a matrix multiplication where the unrolling of the filter and the flattening of the image or vice versa makes it a much simpler matrix multiplication equation to result in the outputs that you want. Right? And how you do that with the dense networks and the convolutional networks. So this is a very good post. And again, post the link to that. It's also there in the notebook. Right. So, so the kernel is the filter that we saw. So this guy is called a kernel or a filter, and this is the image. And the extent by which we move this at a time is the stride. Typically, you may want to pad this image with additional pixels. That's the extent of padding. So these are the terms that you'll begin to see in the use of convolutional neural networks. Right. So let's just start with the very basic X and training and validation images. Let's just say for int. So you say, let's show me the 7th image. It's an image of a 3. Okay. Now I'm going to define, and this is a definition of a filter. Okay. So we are saying top edge, and you'll soon understand why this is called the top edge. So top edge is defined as a tensor of 3 by 3 values. So we saw a 2 by 2. Here he's using a 3 by 3. And a 3 by 3 with these values, -1 on the first row, zeros on the second row, and 1 on the third row. And this, the top edge corresponds, and it's called a kernel or a filter, because that's what kind of computer vision researchers call it. And when we plot this top edge, what we see, because the -1 is a black, zeros are this grayish value, and 1 is a white. So that's why we see a trend towards a black, gray, heading to a white. That's our top edge filter. So the filter will take any window of size 3 by 3 in the images. And if we name the pixels in the actual image like this, you can see what will happen, right? When you lay the filter on top of it, then you will multiply, as I illustrated with the medium post, it'll become -A1, -A2, -A3, zeros, and then +A7, +A8, +A9. Right? So now let's look at what happens when we actually take the 3. Remember, the 3 is a 28 by 28 image, right? Pixel values, and we overlay this particular filter on top of the actual image. And we do that specifically focusing on the 3rd, 4th, and 5th row and the 14, 15, and 16 column. So let's see. So 3rd, 4th, and 5th row, but the 14, 15, and 16 column. So it'll be these 3 values, right? For the first 3, 4, for the 3rd row, this values for the 2nd row, and these values for the 3rd row. Is that clear? What we'll be doing, we'll be multiplying zeros, zeros, and then these 3 values with our filter according to this equation. So because the first 2 rows are zeros, essentially all of this will be 0. The only thing that matters for us is these 3 values, 1, 0.99, 0.99, multiplied by 111, and then we sum. So it will be 1 plus 0.99 plus 0.99. Right? And you can do the math by hand, which is a good thing of why breaking it down to this level helps us understand what's actually. So then if you add it, you get a tensor of 2.9727. The tensor is the result of multiplying the corresponding point-by-point multiplication of the filter or kernel with the values. In this case, we have chosen the values from 14 to 16, and these 3 rows, the 3rd row, the 4th row, and I should go from this row. Right? Now, so this is the value for the 2.9727. Now, if we look at, on the other hand, a different set of rows, so 7th, 8th, and 9th row. So the bottom of this top of the 3. So 7th, 8th, 9 would correspond to, again, 14, 15, 16. So these 3 values, okay, wrong one, these 3 values, right? That will multiply our -1. This will multiply our zeros, doesn't matter because it's zeros. And this will multiply our 1. Again, the value is 0, so that means it will be 0. So because here the filter is 0, so there's 0. Here the values are 0, so it will be 0. So the only thing again that matters is, and that gives us a value of, when we do the filter calculation, of -2.95. So what you begin to see is at the top, we get a very positive value when we take the top edge and we multiply it and use that filter. But when we come down here and use that, then we get a highly negative value, right? Now, this is just on one set of 3 by 3 block that we did on our entire image, and just illustrated what the calculation results in. But what we actually want to do is we want to, as I showed you in the from the post and the images, we want to slide or stride the kernel across the entire image. Right? We want to stride it left to right and then top to bottom, and add up all the calculation to generate the corresponding results of the convolution. So that we do by saying apply the kernel to the row and to the column, and here is the kernel, right? And so what we do here is you take the init tree and we say row -1, because remember there's the row we choose, the row before that, and the row after that. And for the column we choose, and the column before that, and the column after that. So we just do row -1, row plus, from row -1 to row +2, and column -1 to column +2 times the kernel, and then sum it up. So by doing this, we are just applying the kernel to the row and the columns that we specify. Right? And apply kernel for starting at row 4, so 4, 5, and 6. 4, 5, and 6, and then 15, which would make it, I think, oh, sorry, not 4, 5, and 6, 3, 4, and 5, because you go one below that and one above that, and 15, which would mean it'll be 14, 15, and 16. So it just wants to do the same thing, but with programmable rather than hard coding the numbers. Right now, but we don't want to just do the single application of the kernel. We want to apply it to the grid. So a list of lists of all the coordinates of a 5x5 grid, it can be generated like this with a list comprehension, ij for j in the range, and then for I in the range. So you can see that it's generated all of the particular coordinates, if you will. Oops. Right. And so now, if we say in the range of 1 to 27, that is our entire 28 group of pixels, we want to do the top edge 3. So we are applying it to the image 3. So just call it top edge 3. Then convert it to a tensor, apply kernel, and then apply ij in the top edge for j in the range and for I in the range. Right? And the range is always 1 to 27 for both. So what does this line of code do? It just basically takes the kernel that we have and slides it across the image for the image 3 and computes the resulting pixel values. And when we plot it, you can see how the top is white, the bottom is black. Wherever there is a top edge, it detects that. So that's why this kernel has been called the top edge kernel. You can see that the top is top, the bottom. Similarly, we can do a left edge, identical approach, except we kind of define the -1, 0, and the 1s in this way. And so you go from black to white, right? And the left edge on 3, and then you can see you're beginning to detect wherever there is an edge. Right? So that's kind of what applying edges and defining some filters. In this case, we have actually specified the values like -1, 0, 1, and stuff like that. We see increasingly that we don't necessarily need to do that. But one of the things that we can kind of grasp as we do this kernel movement is what happens when we apply a 3x3 kernel to a 4x4 image. Let's look at that. Which one? Yeah, 3x3. No, this is not. Here. Make sure. Yeah, this is the one. Except he shows it with a padding of 1. So we'll get to padding in a minute, but just assume that your original image has been padded with this also 3x3 to 4x4. This is actually 3x3 to a 5x5, but it doesn't matter. You can actually draw the equivalent image for a 3x3 and 4x4 and find out what the result will be. Let me also see who there is. The 2x2 to a 4x4, but the principle is the same. So I'm going to go through this example. So if you apply a 2x2 filter to a 4x4, right, then what results is a 2x2. And the reason is this particular pixel is what you get by applying the filter here then you step one. Sorry, this is a 3x3 filter applied to a 4x4 image. When you apply a 3x3 filter to a 4x4 image, you first place the filter as shown here. That will result in this pixel. Then you slide the filter one step to the right. So you'll go to these set of pixels. That will generate this pixel in the final image. Then you slide the filter down. And so you will now be covering this set, and that will result in this pixel. This set of pixels in the original image. So this is using a 3x3 filter on a 4x4 image will result in a 2x2 output. So one of the things I would encourage you to do if you are in work with it in the past and stuff is making sure that you understand what the resultant output of applying a variety of filters to a variety of inputs are. For example, here's an example of a 3x3 filter applied to a 5x5 image with a padding of 1. So you can see whether you will get a result of doing that will be a 3x3 image. Similarly, you can also consider the case of this is a 4x4 filter applied to a 5x5 image, but with a padding of 2x2 on all sides. That will result in output image of a 6x6. So each of these, work through the math using these images and convince yourself that the result that's shown here is what you get and how you get that. I think that would be a good homework to do. And we're almost at the end, so I think I'm going to stop at this point and we'll start with convolution execution in PyTorch the next time.
Cool. Very nice. Thank you, Srinivas.
Okay. See you all next week. Thanks for joining.
Okay. All right. Bye.
Thank you.
Thank you. Take care.